Hey there, chemistry. So we are still working on being able to describe trends in the properties of the elements. And today we're going to do a little lab activity having to do with one of the properties of the elements in which you see a periodic trend. We've already talked about several different ones, but the one today that we're going to see is a trend in density. And so the lab we're going to do today, it's called Density is a Periodic Property. Okay, before we get going on the lab activity, let's take a look at the lab handout. I have mine on paper here. You've probably got a digital copy. We'll take a look at it here and see what they kind of asking us to do. And there are some pre-lab questions here. So if you take a look, first it tells you a little overview of the experiment. It says that the purpose is going to be to measure the mass and volume for silicon, tin, and lead, calculate their densities, and then use the results to predict the density of germanium. And you're going to see exactly how we're going to do this in a minute here. And then underneath that, you can see there's a little example for how to find the volume of a solid by water displacement. And basically, you see there's the graduated cylinder there. We're going to put some water in there, put the solid stuff in there, see how much the water goes up. And that's the volume of the solid. So pretty simple. And underneath that, we've got some pre-lab questions. Let's take a look at these pre-lab questions. The first one here, it says, one of the elements Mendeleev predicted, he called Eka aluminum, which corresponded to a gap in the fourth row, or the fourth period, of the group 13 elements between aluminum and indium. This is the density of aluminum in period 3 is 2.70 grams per cubic centimeter. The density of indium in period 5 is 7.31 grams per cubic centimeter, and the density of thallium in period 6 is 11.85 grams per cubic centimeter. And it wants us to make a graph of the period number on the x-axis and the density on the y-axis. And you'll see right next to that on your handout a graph that's set up correctly, and I have a copy of it here that I've kind of blown up so that I can show you. And they want us to make a little graph with these numbers in it. So the first one, it gave me some numbers for aluminum. It said aluminum is in, let's see, the fourth row. Or I'm sorry, it's in period 3, and its density is 2.70. So I'm going to come on this graph, and right above period 3 here, I'm going to go up and find 2.70. And of course, that's not marked, but 2.70 is just a little bit less than 3. So I'm going to put a dot right there, a little bit less than 3. And maybe I'll put a little Al next to it so I know that that is aluminum. Okay. And then it goes on and it tells me that indium in period 5 is 7.31. So I'm going to come over here to period 5. And I'm going to come up to 7.31, which is a little bit between 7 and 8. So I'm going to go up between 7 and 8 here. I'm going to put a dot there, and this element was indium, so I'm going to put a little IN there. So I know that's where indium is. Okay, and then the third one I talked about was thallium in period 6. And its density was 11.85. So I'm going to come over to period 6. I'm going to find 11.85, which is just a little bit less than 12. I'm going to put a dot there, and that there is thallium. So I put thallium on my graph right there. Okay. So there's a little graph of those things, and we're going to use this, I believe, in question 2 here. Find the density of the missing one in period 4, which Mendeleev called Eka aluminum. So if you check it out, I'm going to take a ruler. I'm going to make a nice straight line that goes through these dots that I already got here. And it's not going to go through perfectly, but it should go through pretty well. Can you see? And then right here, you see period 4? Right here, that ought to be the density of this missing element. Right there. So then we'll just come on over and read off how much is that on this axis. And let's see, that looks like it's maybe just a little bit more than 5. Maybe it's 5.5. So on number 2 there in these pre-lab questions, I'm going to answer the question. I'm going to say, oh, it's about 5.5. And then it wants us to go and look up what the actual value is. So that element that we're talking about here is, let's see, which one was it? Was it germanium or was it gallium? Echo aluminum. It's right below aluminum. It was gallium. So we'll go to a reference, or we'll go on the internet and we'll look up what's the density of gallium. We'll look up what's the density of gallium, and we want to make sure that we look it up in grams per cubic centimeter. And I looked it up there, I got 5.1. So here in my graph, I predicted it would be 5.5. I looked it up, it was actually 5.1. So that's pretty close, right? Just from a graph, I predicted it. So pretty close there. Okay. And now, number 3, it says, how do the actual and predicted density values compare? Are they close? So, you know, I said 5.5. It was actually 5.1. I would say that's pretty close. Okay, so now we just did that little example there with aluminum, gallium, or the other ones, indium and thallium. And now we're going to do kind of the same thing with the next row over. I have here the next row over there, you know, it starts with carbon. And then below carbon, you've got silicon. Below silicon, you've got germanium. And we're going to try to find the density of germanium. Below germanium, you've got tin and lead. So what I'm going to do is I'm going to find the densities of these. I'm going to make a little graph. And then we're going to predict the density of germanium. And then we'll go ahead and look it up and see what it actually is. So you'll notice I'm not wearing my snazzy goggles because there's really nothing here that's going to get in my eyes. So it's not a particularly dangerous lab. So I have chosen to forego my snazzy goggles today. So I got my lab handout here. I'm going to see what the instructions tell me to do. The first one, it says we're going to label 3 beakers or small containers with silicon, tin, and lead. And I have some little weighing dishes that we'll use. It says measure the mass of an empty beaker and record it in the data table. So this first one, I'm going to measure the mass. I have here a scale. And this is 2.47 grams. So I'm going to take my data table, and you guys can find this in your handout. I have here my data table. And this is the mass of the beaker, which is 2.46 grams. Okay. Now my instructions now say, obtain approximately 8 grams of silicon chunks. So I'm going to open my bottle of silicon here, and I'm going to pour some out here. Now, having done this lab before, I know that sometimes these little bits of silicon might be bigger than the top of this, so I'm just going to kind of check and make sure they're not. And these ones are good. So it says we want about 8 grams. So here, let's put this on here. Maybe a few more. That's probably pretty good. Okay. So now this is, right now it says 12.52 grams on my scale. So it says measure the combined mass of the beaker plus the solid. So in my first box on my data chart, I'm going to put 12.53 grams. 12.53 grams. All right, now, the third step, it says fill a 25 milliliter graduated cylinder, about half full with water, and measure the initial volume of the water in our data table. So I'm going to put some water in here. And sometimes we might use distilled water, but for this particular activity, it doesn't really matter. I'll just use tap water. Okay, so I have very carefully filled it up to about 15 milliliters. So on my data table, I'll record the initial volume as 15 milliliters. And then what we're going to do, what is it, step number 4, I think? Add the silicon chunks to the graduated cylinder. Add slowly so we don't splash. So I'm going to dump my silicon in there. And now you'll notice the water level is higher. Step number, what is this, step number 5? Measure the final volume. So now I'll read off the final volume. Let's see, that's 15, 16, 17, 18. Looks like just about 19 milliliters. So in the final volume, oh, I put that 15 in the wrong spot. I put that 15 in the wrong spot. It should be right here. So I'm going to put that 15 in the right spot. And now it's at 19, so I'm going to change my 15 there to 19. Pretend that says 19 really nice. Okay. So now that is that for silicon. Now we got to repeat all of these steps using tin instead of silicon. So I'm going to, again, take my weighing dish. I'm going to put it on here. This one weighs 2.55 grams. So I'm going to put that under a massive beaker, 2.55. Now we want to get about 8 grams of tin. So we're going to pour this in here. This is the pieces are a bit smaller. Ooh, that's way more than 8. Okay, that's okay. The exact amount doesn't really matter. This is now 17.10 grams. So I'll put that under massive beaker and sample. 17.10 grams. Put some water in my graduated cylinder. Yeah, that's really good. Okay. So we're at about 15 milliliters, and that is the initial volume. I'll put it in the right spot this time. And then I'll put my tin in there. And now you can see the water level's gone up. It's now at 15, 16, right about 17 milliliters. I don't know if you can see it in the camera. It's right about 17 milliliters. So we'll put that for the final volume. Okay. And then the last one here, it says PB on the data sheet. PB is lead. So I'm going to take another weighing dish, put it on my scale. It's 2.40 grams. So I'll put that for the mass of the beaker. 2.40. Now we want to get some lead in there, so I'm going to take my lead. This is about 8 grams, but you know, it really doesn't matter exactly how much. Now the lead, if you're doing this lab in real life, this lead, it's these tiny, tiny balls of lead. They run all over the place if you spill them. So please do not spill them. Probably that much is good. I don't know. Now this is way more than 8 grams, but that's okay. 43.56 grams. I'm going to put that under mass of beaker and sample. 43.56. Okay, now I'm going to get some water in my graduated cylinder. Now I've been filling it to, you know, pretty much exactly 15 to start. Does it need to be that? No, it could be really anything. Just something to start. Just kind of makes it a little bit easier for it to be pretty close to exactly something. Makes the math a little easier later. Okay. I'm going to say that's pretty close to 15 right there. And then we'll put our 43 grams of lead in there. Well, this is actually more like 41 grams of lead because the weighing dish weighs 2. So being very careful not to spill lead all over the place because It will run everywhere if I do. Here we go. You can see the lead's in there, the water level's gone up, and it's now, I want to say that's about 18.75. So my initial was 15, I filled it up to 15, and my final 18.75. All right, so now we have completed all of the data it asked us to take. Now we still have to do a little bit of math and figure out these other parts. But yeah, at the moment, I'm gonna put some stuff away so that it's not in my way. And then we'll go ahead and we'll take a look at our data after that. Okay, let's now go ahead and complete the table. Like it says in, what is it, Postlab calculations. It tells you how to complete the table here. First, we're going to figure out this column here, the mass of the sample. And to do that, we're going to take this one and subtract this one. So we're just going to subtract these two numbers. And I have my trusty calculator. And for the first one here, for silicon, 12.53 minus 2.46 gives me 10.07. For tin, I have 17.10 minus 2.55. And I get 14.55. And then for the lead, I have 43.56 minus 2.40. That is 41.16. Okay. Now, this number is going to be important when I go to figure out this last one. Okay. Now let's figure out this one. To figure out this one, we're just going to subtract these two numbers. I'm going to take the final volume and subtract the initial volume. And so that should be pretty easy. For silicon, we have 19 minus 15, which is 4. For tin, we have 17 minus 15, which is 2. And for lead, we have 18.75 minus 15, which is 3.75. Just like that. And then to find the density in this last column, we're going to take the mass divided by the volume. So we're going to divide these two, and that'll give us the density. So for silicon, I have 10.07 divided by 4. And I get we'll just round this off to 2.5. For tin, I have 14.55 divided by 2. And let's see, we'll round this off to 7.3. And then for lead, we have 41.16 divided by 3.75. And I get 10 point, we're just going to round that off to 11. Okay. So now I have the densities of my three materials here. 2.5 grams per cubic centimeter, 7.3 grams per cubic centimeter, and 11 grams per cubic centimeter. Now, number 3 in the Postlab questions is going to ask me to make the same kind of graph that we made before we did the lab. So I'm going to do the same thing. And I'm going to predict the density of the missing one, the one that's in row 4. So the first one we have on here, silicon. Silicon is in row number 3. It's in period 3. So I'm going to go to period 3 on my graph, and I'm going to go up to its density, which was 2.5. And I'm going to put a dot there. So period 3, 2.5. That right there is silicon. Okay, the next one, tin, SN, is in row number 5. So I'm going to go up from period 5 to 7.3. 7.3 right there, and that is tin. Tin is SN, by the way. And then the third one here, lead, which is PB, by the way, is in row number, where are we at, number 6. So I'm going to go up from there to the density of lead, which is 11. And there's lead. And now let me take my ruler and draw a nice pretty line that goes right through all three of those dots. And maybe it doesn't go exactly through all three of those dots, but it goes through pretty close to all three of those dots. And so now I'm going to go up. Which one is in period 4? And I'm going to see how much is that on the y-axis. And that looks pretty darn close to 5. So I'm going to say that the density of this missing one that's in period 4 is really close to 5 grams per cubic centimeter. So, and which element is this? This is germanium. So I'm going to say it's really close to 5 grams per cubic centimeter. That's my prediction. So now what I'm going to do, what it asks me to do, is go on the internet and look up what is the density of germanium. And Google tells me it is about 5.5 grams per cubic centimeter. So was that pretty close? I said it was pretty close to 5. And Google says it's 5.5. So I'd say that's pretty close. I think we're a little bit low there, but that's all right. It's pretty close. And let's see, that looks like that is the lab. So that's it. All right, so that was the density is a periodic property lab. You can see that the densities of the different elements as you go down the column increase in a nice straight line kind of way, which makes it easy to predict a missing one, right? So hopefully that gets us one step closer to being able to describe the trends in the periodic properties.